Hello everyone. Today we discuss the moment of inertia of a spherical shell.
Now that the problem is, first of all, we to know about what we mean by the inertia, simple inertia. Inertia comes into play whenever there is a linear motion. The inertia means inability or the inertness on a part of the body to change itself, its position, either of rest or of uniform motion. Body is helpless to change itself, its position. It is the inert, you can say it is the inertness of the body. It cannot change itself, its position, either of rest or of the uniform motion. That means to change the position, the state, position of the state, that either of rest or uniform motion or the direction, we to apply the force. Force is required in that case. Similarly, what is the moment of inertia? Moment of inertia comes into play whenever there is a rotation. In a rotation, like if we try to rotate a body, the body will resist. Then we to apply the force to rotate it. And if the body is already rotating and we want to stop it, then again we to apply a torque to stop. When the body is at rest, it's not rotating, it cannot rotate by itself, then we have to apply a torque. Torque is made up of radius and force. So we need a torque to start the rotation. But when the body is already rotating and we want to stop it, then we have to apply again the retarding torque to stop it. Then the opposition which the body gives, maybe in linear motion, maybe in rotation, that is inertia. But in linear motion it is called simple the inertia. In rotation it is called moment of inertia.
Today we have taken a spherical ball. First of all, we will know what is a spherical ball. It is a hollow sphere with very negligible, or you can say very little thickness. First of all, we will cut this spherical ball into such a way that we can get a ring. We will find the moment of inertia of this ring. Then further, we will integrate it to find the moment of inertia of the whole spherical shell.
Already Simon told you about it. What was mean by the spherical shell? The spherical shell means it is a sphere, hollow sphere, okay, but of very, very small, equals to the radius. And this is elemental part which we cut already. Okay, this is one elemental part. It is in a form of a ring. This ring, from the center of the spherical shell to the ring, like that at this position or this position, the radius is the same, that the capital R. Okay? The radius is the same. This is capital R. This one is capital R. And this one is again the capital R. But the angle encloses by the two ends, like this one and this one. The angle encloses, it is d theta. From here to here is d theta. And you will say, then you may have a question, what is theta? Theta is actually, this is like R. The theta angle is this one, from here to here. Okay, this angle encloses, it is equals to theta. This angle is theta. So it is clear in the picture. Hello, it is clear. This angle is theta. Okay, sorry. This angle is theta. Now from here to here, the angle is d theta. Now we have to find the moment of inertia of this ring about We have to find the moment of inertia of this ring about this axis. And what is the formula of the moment of inertia? This mass of this ring multiplied by this radius. This one, this is not capital R. This radius small r. So its moment of inertia is mass into small r the whole square. Now what is the mass of this elemental ring? So let I cut it. Now this length is 2 pi into small r, and this one is, how much this one is what, capital R, because angle is arc over radius, angle is d theta, this is a arc, d theta is equals to arc over radius is capital R. The arc, this arc becomes this arc, capital R into d theta. This arc is capital R into d theta. Now what is this surface area? This surface area is, this length is 2 pi small r. 2 pi small r into capital R d theta, which is this arc. That becomes the surface area of this elemental ring. Now the total mass of the sphere, mass of the spherical shell is capital M, and mass of the sphere is the mass of the spherical shell is capital M. Surface area is 4 pi capital R square. Then what is the mass per unit surface area? M upon 4 pi capital R square. Now if we know the mass per unit mass, mass per unit area, if we know mass per unit area of the spherical shell, then we can find mass of the, this elemental ring, because we already know what is the surface area of the elemental ring. Now then we do the calculation and we can find easily the moment of inertia of the spherical shell. How? By integrating, because the spherical shell is supposed to be made up of very large number of these type of the elemental rings, which whose radii extending from very small value to the large values, going from top to the middle, and then again when we move from middle to top, again the radii of the elemental ring decreases. The moment of inertia of the spherical shell about the axis passing through its center as well as through its center of mass. So this is our spherical shell, okay, and this one is the radius of the spherical shell. The angle, we consider a very small element. We consider a very small element of thickness, the angular thickness, it is d theta, and the radii equals to smaller. This radii is smaller. Now this is parallel axis, parallel to smaller, then perpendicular to the, this baseline. Then angle encloses of the elemental ring with the baseline is theta. This is, like OA, it is r cos theta, because radius is r. The right angle triangle based upon hypotenuse is cos theta. So small r becomes capital R cos theta. Then, angular width of the elemental ring, angle is arc over radius. Then we find that the arc BC equals to capital R into d theta, right? This is angular width, capital R into d theta. Spherical shell is supposed to be made up of very large number of these type of elemental rings, extending from minus pi by 2 to plus pi by 2 from the baseline OA. Now we have to find moment of inertia about the diameter passing to center as well as to center of mass. Now what is the mass of the shell? Mass of the shell is, what it is. Mass of the shell is capital M and its surface area, whole surface area is 4 pi r square. Then you find mass per unit surface area, that capital M divided by 4 pi r square. Then we consider one elemental ring. One elemental ring of width equals to r into d theta. Now, what is the surface area of the ring? This is a problem. Now, surface area of the ring is that the circumference multiplied 2 pi r is circumference multiplied by the width. That is capital R into d theta. Now, we know already what is the small r in terms of capital R. Small r is capital R into cos theta. So, substituting it here, and then surface area becomes 2 pi capital R cos theta into the value of small r, and it becomes surface area of the ring. Now we are finding the mass of the ring. Mass of the ring is mass per unit surface area multiplied by surface area of the elemental ring. So just substituting the values. So this is the mass of the one ring element. Now we are in a position we can find now the moment of inertia of the one such ring, considered ring. Now we are in a position to find the moment of inertia of this ring about the diameter of the spherical shell. So what it is, the formula is mr square, mass of the elemental ring multiplied by the small r square. Elemental ring, is moment of inertia. So that's the r square means small r square. Now this is a small moment of inertia of one ring. This type of rings, they extend from the baseline minus pi, is a baseline minus pi by 2 to plus pi by 2. Minus pi by 2 to plus pi by 2. So integrating within the limits. So minus pi by 2 to plus pi by 2. Now because it's a cos cube theta, and now splitting it. Splitting the cos cube theta. Cos square theta into cos theta. Okay, now, so splitting cos cube as cos square and cos square theta is 1 minus sin square theta. Now then, substitution. Substitution is, let me put sin theta equals to t, and differentiating it, cos theta d theta becomes equals to dt. And, the limits will change. Before it was minus pi by 2 to plus pi by 2. Now it will be minus 1 to 1. So the moment of inertia becomes minus 1 to 1, and then 1 minus t square into dt. Now this integration is very simple. The result is t minus t3 by 3. Our limits are minus 1 to 1. Now substituting the limits, then we'll get the moment of inertia of the whole spherical shell above the diameter, which is passing to the center of mass of the shell. So the result becomes equals to 2 by 3 mr square. Now lastly, this is the moment of inertia above the diameter. Now we are interested about the tangent touching the spherical shell shown in the figure, like IT mean about the tangent. Now applying the theorem of the parallel axis. So this theorem states that the moment of inertia about the parallel axis mean tangent is moment of inertia about diameter plus mass of the shell into perpendicular distance between the two axes. That's again the capital R square. So the formula becomes I equals to 5 by 3 mr. Please subscribe my channel, is my request. Thank you very much.